Now let's go back to Gauss's law. Gauss law is actually an expression of the general relationship between the net electric flux. So that's why we discussed first about the electric flux through a closed surface and the charge enclosed by the surface. So that's why I highlighted earlier, you have your flux E that is equal to your Q over your epsilon naught. The closed surface, the imaginary surfaces that we have earlier, the imaginary box, the imaginary sphere, we often call those as your Gaussian surfaces or your Gaussian surface. Gauss law is fundamental importance in the study of electric fields, and we usually use this one when we have symmetries in our systems. Now for your Gaussian surface, closed surfaces of various shapes can surround the charge. As I've said earlier, the shape of your Gaussian surface does not actually matter if you just want to find for the flux on your system. Here you see that only S1 is spherical, okay, and S2 is another irregular shape, while S3 is also another one. But from this case here, for your S1, S2, and S3, you know now that the flux is just the same for the three surfaces. It verifies that the net flux through any closed surface surrounding a point charge Q is given by just your Q over your epsilon naught. And this is independent of the shape of the surface. As we've discussed earlier, for the three shapes here, for S1, for S2, and then for S3, you just have the same flux, which is just equal to your Q over your epsilon naught. So the shape of your Gaussian surface does not matter here. However, if the charge is outside the closed surface with an arbitrary shape, any field line entering the surface leaves at another point. So for this case here, the flux is 0. Okay. One thing is not enclosed, and then the other thing is that the flux flowing through here inside just goes outside the other way. So it verifies that the electric flux through a closed surface that surrounds no charge is 0. The mathematical form of Gauss law is this one. So earlier you have this one here. This is for your flux, right? We use this one for your flux. Okay. And then this one here is your Gauss's law. So this is actually one of the equations of Maxwell's equation, which we hope to be able to complete during this course. So this is again the mathematical form of Gauss's law. It states that the flux of E is equal to your surface integral E dot dA, which is just equal to your Q enclosed over epsilon naught. Your Q enclosed is the net charge inside the surface, or the charge enclosed by the surface. And although Gauss's law can in theory be solved to find E for any charged contribution, in practice it is limited to symmetric situations, because it will be hard for us to solve the electric field when using Gauss laws when there is no symmetry in your situation. To use Gauss's law, you want to choose a Gaussian surface over which the surface integral can be simplified and the electric field be determined. The key word here is that we should take advantage of the symmetry. And remember that the Gaussian surface is a surface you choose. It does not have to coincide with a real surface. These are examples of Gaussian surfaces where we are taking advantage of the symmetry. Let's say, for example, for a point charge, just for a point charge, we use a spherical Gaussian surface, because for a point charge, your electric field is radially outward, right? Okay, and if we have a Gaussian surface that is spherical, as you can see here, your electric field is always perpendicular to your vector A. So if that is the case, you have the maximum of your flux. The same is true for a conducting sphere. Okay, for a conducting sphere, this is a sphere of positive charges. We use a Gaussian surface of a sphere of shaped sphere. Also for a sphere with uniform charge density, if this is like a volume, you have your rho. Okay. For a line charge, we use a cylinder as a Gaussian surface. Why is it? Because here, if this is a positively charged line charge, your electric field is like this. Okay, radially outward again. And anything here, anything on this side here, any field that goes here will have a zero contribution. And here, since these are radially outward, your E and then your A are also perpendicular. Okay, the same case for your conducting cylinder and then a cylinder with uniform charge. We use a cylindrical Gaussian surface. Now for a charge of sheet, you have this sheet here. Let's say this is positively charged plus. If this is positively charged, your electric field will be outward and then downwards. Now what we use here is still a cylinder, okay, but there are no charges or there are no field lines along the corners. So all that is left here is just from the top of your cylinder, which has a vector A upwards, and then your electric field are also perpendicular. So E and A are also perpendicular here. The same is true for a charge on the surface of a conductor and for a charge conducting plates. So we always take note of the symmetry when you're going to use your Gauss's law. Let's have here an example. So find the electric field at the distance r from a line of positive charge of infinite length and constant charge per unit length lambda. So earlier we have a line charge. If you can remember, we solved for a line charge, and then in that line charge you have we find for the electric field at some field point P, and we use some tedious integration to solve that one. But here we just use your Gauss's law. That is, your flux E is equal to your integral of E dot dA, and you can take outside your electric field E. Take outside of the integral, so you have your E close integral dA. Now, here your A is your Gaussian surface, the area of your Gaussian surface. And as you can see, the electric fields that give contribution are only these fields here. Okay, and then again, these are radially outward, of course. And your Gaussian surface is a cylinder, but the top one and then the bottom circles do not have a contribution. The only thing that gives contribution is this side here of your cylinder. And the area of that one is you have if you're going to break that one out, you actually just have a rectangle that is folded to turn into like a cylinder. So this one here, the length is 2 pi r, which is for this circle here, and then this length is your L. So that is the area. So we use this one here. The charge enclosed, Q enclosed, is your lambda L, again because this is a line charge density. So we actually just have your EA that is equal to your lambda L over epsilon naught, and your A is 2 pi RL, your length times width. Okay, so you have this one here, this equation. You have you have E 2 pi RL that's equal to lambda L over epsilon naught, and we can cancel out some terms, your L here. Okay, and then we can transfer some terms to the other side, and we have this equation here for your electric field. This is easier compared to what we did earlier using your Coulomb's law. Let's try to review. So you have this one here. We solve this one using a tedious integration, and then we get this answer if a is greater than x. Okay, but you can actually compare this one to this equation, right? Here you just have your x because we are referring to your x here, and here you have your r because any point r from this cylinder. So they're actually just the same equations. But this one, you did some long integration. And here we just use your Gauss law, which is you have your EA, your Q enclosed over your epsilon naught. Important also to this discussion is your charges on the conductor. Well, basically, the charge on your conductor says that the excess charges resides only on the surface. So it's just on the surface of your conductor. If you have a cavity inside the conductor with Q equals 0, meaning like this one here, there's no charge here in this cavity. E is 0 inside the conductor. So there's no electric field inside this conductor here. And all the net charge resides on the surface of the cavity. Again, it's just outside. This one here. It resides on the surface. It resides also on the surface. Electric field is 0 inside of your conductor. That's always the case. Inside your conductor, your electric field is 0. Even if there is a cavity here, the electric field is also 0, and all the other excess charges resides on the surface. If you have a cavity inside a conductor with plus Q, like this one here, you have electric field is 0, is still inside the conductor. And then the charge on the surface of the cavity drawn there by plus Q. So you have some negative charges here because your negative charges is attracted to your positive charge Q here. And the total charge inside the conductor is still 0 because these are just balanced out. Okay, it's just that your negative charges were attracted to your plus Q, and then the other on the surface of your conductor. Okay. Some basic properties of your conductors, which is basic electrostatic properties of your ideal conductors. E is again 0 inside the conductor. Why? Because if there were any field, those free charges would move and it would not be electrostatics anymore. By the way, what we are discussing now is electrostatics, meaning charges that are at rest. And then Q inside is 0 inside the conductor. There is still charge around it, but exactly as much plus charge as minus. So net charge in the interior is 0. So of course you have charges inside the conductor, but it's balanced by your plus and then your minus. So it's basically the net is 0. Any net charge resides on the surface. That's the only place it can be. Why? Like any other free dynamical system, the charge on the conductor will seek the configuration that minimizes its potential energy. So the potential energy will be minimized when they are inside here or they are residing on the surface. There will be greater potential energy when they are inside because there will be more repulsion and attraction that will be existing. So they wanted to minimize the potential energy, and that is by residing on the surface of your conductor. A conductor is an equipotential surface. You will know more about equipotential later. And then the electric field is perpendicular to the surface just outside the conductor. So just like here, anywhere around the surface, the electric field is perpendicular. Again, the important point here is that the electric field is 0 inside the conductor. Q is 0 also inside the conductor. And all the net charge resides on the surface. Okay, so let's have an example. You have concentric spherical shells. So these are spherical shells which are concentric. One of the shell is smaller than the other. A small conducting spherical shell with inner radius A and outer radius B is concentric with a larger conducting spherical shell with inner radius C and outer radius D. The inner shell has a total charge of plus 2Q. and the outer shell has a charge of plus 4q. Calculate the electric field in terms of q and the distance. In terms of q and the distance are for the following. A, you have r is less than a. And then B, you have a is less than r is less than b. And then C, you have b is less than r is less than c. And then D is C is less than r is less than d. And then E, r is greater than v. Your r here is again the radius of your the radius. Okay. So two concentric circles, spheres, two concentric shells, I mean, and your inner shell has a charge of plus 2q. Your outer shell has a charge of plus 4q. You're going to find for the electric field at this point here. Again, your Gauss's law is just the integral of your E dot dA, and then this is equal to your Q enclosed over your epsilon naught. Now let's solve the problem. For the first problem, we are asked for the electric field when R is less than A. So since these are spherical shells, our Gaussian surface is of course your Gaussian surface is of course spheres. Okay, so let's draw your Gaussian surface. So the first one is inside R is less than A. So your Gaussian surface is just inside here, a sphere of radius R. There's no charge inside. Okay, so your E dot dA, your integral of E dA, Q enclosed over epsilon naught. Your E and then your area is just a sphere, so you have 4 pi r squared. You have Q enclosed over epsilon naught. There is no Q enclosed. Your Q enclosed is 0, so that means the electric field at that point is equal to 0. Okay, so that's how easy your Gauss's law is. Next, let's solve for when your A is less than R is less than B. Where is this? So for this case here, this is actually inside your spherical shell. And what have we learned for your spherical shell, for your conductors? For your conductors, anywhere inside your conductor, the electric field is automatically 0. So that is the electric field inside your conductor. Again, anywhere inside your conductor, the electric field is 0 automatically. So next, let's solve for C. C is when B is less than R is less than C. So meaning that is somewhere around here. Okay, so this is now where your Gaussian surface is. So let's just use directly your E 4 pi r squared Q enclosed over epsilon naught. What is Q enclosed here? You are actually enclosing this one with plus 2Q, right? You have plus 2Q there. So that is what you are enclosing. So you have E is equal to 4 pi r squared and then 2Q over epsilon naught. Or your electric field E is equal to Q over 2 pi r squared over times epsilon naught. So that is your electric field at B is less than R is less than C. Next, let me erase these things here. Okay, let me just erase this one. This will not take long. So for the next problem, you're asked for the electric field. Let me just write around here. Letter D. The electric field when C is less than R is less than D. Meaning your Gaussian surface is here, inside your conductor. Since we are again inside of the conductor, your E here is automatically 0. Even though you may agree, uh, you may disagree with me because you have here your plus 2q, right? But again, we are looking at our Gaussian surface is inside a conductor. So whatever there is in here, it doesn't matter because we are inside a conductor. And again, inside a conductor, the electric field is 0. So here, your electric field is 0. And then lastly, letter E. What is the electric field when R is greater than D? Meaning, what is the electric field when your Gaussian surface is enclosing your two spherical shells? So you still have your E, 4 pi r squared, your Q enclosed over epsilon naught. What's your Q enclosed here? You have your plus 2Q, and then here you also have your plus 4Q, right? So we now have two spherical shells enclosed by your Gaussian surface. So we need to add these two, so you have plus 6Q. So you have here 6Q over epsilon naught. So you get this electric field E of 6Q over 4 pi r squared epsilon naught. Okay. So that ends our lesson on your electric flux.